431, we are introducing our rules and properties for exponents and polynomials. So we'll go through a couple of the proofs and then focus on some example problems. The first of our rules is working with constants and functions when we take the derivative of them. So what you see highlighted is the rule. What you have above is the proof to it. So here they're showing you that this would be the derivative of c times some function f of x. Using our limit definition of a derivative, it would take on the same application, that f of x plus h minus f of x, except we're adding the c. And then you notice the third step, we factor the c out, and then if we can pull it out here, then I can just pull it outside of our limit function as h approaches 0, and we are left with rule number 1, that the derivative of c times a function is the same as c times the derivative of that function. Let's do two quick examples. So starting with this first one, if we're asked to find the derivative of 7x to the 5th, we are going to go back and remember the power rule that told us that if I had the derivative of x to the nth, that would be n times x to the n minus 1. So going back to 7x to the 5th, that's the same as saying 7 times the derivative of x to the 5th, which would be 7 times 5x to the 4th. So our shortcut is, when we see 7x to the 5th, we can just take that exponent and multiply it to the constant, the coefficient, and we have 35x to the, and we lower that power by 1. For that second example, they're asking us to take the derivative of 8 over root x. So what we want to do is write that as an exponent, which would take me to this step. So then my next step, just so that I have it in that x to the nth form, I would write that as the derivative of 8x to the negative 1/2. So now I can apply my power rule and say that would be the same as x, or 8 times negative 1/2 x to the, and I decrease that exponent by 1, and that leaves us with x to the negative 3/2. We can then clean that up a little bit, and we have negative 4. I could write that as negative 4 over the square root of x cubed, or I could just write it like this. Our next rule tells us, and I'm going to highlight it, if I have the derivative of the sum of two different functions, that is going to give us, and then you'll see right down here, the same as taking the derivative of one and adding it to taking the derivative of the other. This also works for subtraction too. So let's go through, and I wrote down all the steps just to save us time, but let's go through what that would look like if we were to use our limit definition. So you'll notice in red, this is just us plugging in the x plus h's for all of the x's, and then subtracting from it the f of x, and then putting it all over h. So this is our limit definition, but then replacing that single f of x with f of x plus g of x. So it would look like this. So you'll notice in blue, there was some grouping that was done. So in blue, we grouped the f's together. So we had f of x plus h minus f of x, and then we grouped the g's together. So that was just us rearranging some of the terms. And then you'll notice in green, we just split them up because we can. It was just a monster of a fraction, so we separated the f's and then we separated the g's, and we kept that limit as h approaches 0 for both of them, and then identified with that what's in green is the derivative of f, and then here, that's the same as the derivative of g. So with that application, that means if I have multiple terms within my expression and I'm asked to derive it, I can derive each one independent of the other. So here's an example of one. If we were asked to derive that expression, we would use our power rule. So we'd notice that, and at some point you're going to stop taking this step and just doing it very quickly. So you'll just jump straight to seeing that you're going to bring the 4 down and multiply it to the 3, and then lower that power by 1. So that's 12x cubed for the first term. And then here we would then rewrite that cube root of x exponentially. So that would be 5 times x to the, and then this is power over root. So 5x to the 1/3. So when we derive that, I shouldn't have put that in that place. That hasn't been derived yet. So now we would end up with 5 times 1/3. So that's 5/3 x to the, and then we lower that power by 1. So 1/3 minus 1 gives us x to the negative 2/3. So here are a few problems. Okay, more than a few. And pause it here and see if you get the same results. So here are the answers to the 7 problems. And if you are comfortable with those, then perfect. You can end the video now. Otherwise, stick around and we'll go through just bits and pieces of most of them. So I believe one is fairly intuitive. The one thing I do want to remind you of is that the derivative of a constant is 0. And remember, I can think of it as negative 13x to the 0 if that helps, and then we could still use that power rule. And we would end up with 0 because it's 0 times, we don't care, 0. So let's look at some of the others. For 2, I would rewrite that expression first so that it was in power form. I want it to read as an exponent. So we would have the derivative of 4x to the negative 3. And that's how we end up with negative 12x to the negative 4. And you noticed here that I put both notations. You can have it as a negative exponent, or we could rewrite it as with a fraction. And then you'll see that 3 takes on that same idea. We would rewrite that so that they were both in exponential form, and then we could apply the product rule accordingly. Now, if we looked at problem 4, again, I would rewrite this. We are deriving with respect to x, so I'm going to separate those 2 terms. So 4 could look like this. And remember, folks, we're deriving with respect to x, which means I'm going to treat a, b, and c as constants. So I can identify that with that first term, a over c is the coefficient of x, and then b over c is just some constant. So if we were to derive that, that's how we end up with that solution of just a over c, because the derivative of that constant is 0. Now, if we looked at 5, we would treat it the same way we did 4. I would separate those 2 terms so that it looks like this. And then we could simplify them before we derive, and it would look like so. And now we can see that we've got the derivative of this constant a over c plus b over c times x to the negative 1, and that's how we end up with our solution, and both of those are fine as answers. Now for 6, we haven't yet learned the rule for multiplication when we have the product of 2 terms, so we would first with this one distribute that root x to both terms, and I would write it first exponentially. So it looks like this. Now, don't forget the fact that when I'm distributing and I've got like bases, I add the exponents. So then that simplifies to give me this. And now I'm ready to derive, and that's how we get our, oh, it's right there, 5 halves x to the, and we lower that exponent by 1, 5 halves x to the 3 halves. Now, 7 is pretty much the same idea as the others. 9x squared, that derives to give us 18x, Pi is a constant, so I know the derivative of that is going to be 0. The derivative of 7x is 7. And then this last term we would write as 2x to the negative 1/3. And when we derive that, that's how we are left with 2/3. And it was minus 2, so, I should add that too. And that's why we have positive 2/3 x to the negative 4/3. And that's 3/1.